The challenge is that tuning these tends to be more art than science because there hasn't been a very good curriculum.
PID is an acronym. Proportional integral and derivative is really what it stands for. And of course, that's a majority of what type of control is out in industry. And you see the second bullet there, more than 9 out of 10 controllers in service today are PID. Now, that doesn't mean that there aren't extra programs or other caveats in your program to maybe limit the movement of a valve, or perhaps you're taking care of a disturbance. But in the majority of cases, you'll find that PID is very prevalent. And so it's important to know and have in your skill set, your tool set, the ideas behind the methods to tune ever chasing PID.
PID isn't going anywhere, right?
Yeah.
It's across all the different industries. It's really inexpensive, as Jack mentioned. I mean, you can get standalone single loop controllers, in Arduino code for $100, right? And the challenge is that tuning these tends to be more art than science because there hasn't been a very good curriculum. There's not a lot of good formal training, in the US at least. There's not a lot of good process control training classes for the engineering team. It's a 1 semester theoretical class that covers Bodie and Nyquist and stability and all this stuff, and they don't actually have to teach you how to tune a controller, which is always really disappointing. He took a controls class and he was like, I'm so excited. And he's like, Dad, we spent 1 day talking about a PID controller and we never even tuned them. He was so disappointed. And I was a little disappointed as well, right? So the trial and error method really just remains common. And that means that every engineer has a different method, a different strategy, and you can get very inconsistent results, right? You get 20 people in a room, you get 20 different answers. And from a consistency standpoint, that's not a good thing.